Hello and welcome to the second lecture for Math 232. This is section 1.2, span and linear independence. Both of these things, span and then separately linear independence. We are going to be using these things repeatedly throughout the course. So like we discussed in the first lecture, knowing what these words mean precisely is going to be highly important. Let me just because I find this interesting, point you to this quote. So this is a quote by Alexander Grothendieck. You should just pull up the Wikipedia entry on this person and just have a look at that. This is a tremendously productive and probably one of the best mathematicians of the 20th century. So certainly somebody whose name you should be familiar with, and you might just find it interesting to read about him. Okay, so again, we're going to do a little bit of the vocabulary that we're going to be using to talk about all this stuff. And so we have the something called a trivial solution. That means the solution consists only of the zero vector, or the zero, maybe not necessarily only, I should say, but one of the solutions is the zero vector, and we call that solution the trivial solution. A unit vector. So if we say something is a unit vector, that means it's a vector of length 1. Span, again, important, and we're going to go in detail of what this is below. Standard basis vectors. So the standard basis vectors, we'll get a little bit more in depth on this. We'll learn what the word basis really precisely means, but what the standard basis vectors are in R2 are these two vectors, E1 and E2. Often that is what they are called. And just so we see what they are, they're basically the unit vectors along the axes. So E1 is this vector here. And with this number here being 1, that's the x-axis and the y-axis. And this vector here is E1. And then we have another vector here, which is at right angles to the first vector. This is also here 1 along the y-axis. And this vector here is E2. So those two vectors taken together in R2 are called the standard basis vectors for R2. We're going to see exactly why it's the word basis is there shortly. Similarly, the standard basis vectors in R3 are these here, and those are also the length 1 vectors along the axes. So in R3, this looks like this. We have 3 axes. It's a 3-dimensional space, and we have here x, y, and z, and we have E1 being this vector right here. Sorry, let's do that again. We have E1 being this vector here along the x-axis. That is the vector 1 on the x-axis and 0 and 0 on the y and z axis. And then we have here the vector E2, and then we have this one here, and that is vector E3. And they're all at right angles. In pairs, they're at right angles to each other. So E3 is at right angles to E1. E3 is at right angles to E2, and E2 is at right angles to E1. Those are the standard basis vectors in R3. Another concept we're going to come to in this lecture, we just have it here because it is very important, linear independence. You must understand what that means. And then we have this word basis showing up here, which is defined in terms of the span actually above. So again, we'll see what that is there. So let's start with the definition of a span. Here's the definition. If we have some vectors, there they are, V1, V2 through to Vs in R2 or R3, then the set of all linear combinations of those vectors is called the span of those vectors. Okay, so it means the set containing, let's take a look at what this thing here says. The set of vectors, which we're calling X, set of vectors X, where X is equal to all the linear combinations of vectors V1, V2, V3. And those constants T1, T2, etc. are real numbers. Okay, so that is the definition of the span. But let me just give you a hand-waving geometric impression of what the span is. And let's do that in R2. Let's imagine we have two vectors in R2. Okay, so here's Here's R2. We have vector. Let's just do it like this. V1, and we have vector here, V2. Okay. And then we say, what is the span of V1 and V2? It basically means where can you get to by walking along V1 and V2. And what do I mean by that? Let's just sort of consider a path of moving along. So I could move some distance along V1 like that, maybe another V1, and then I can move along V2, and then I can maybe move along minus V1, and then I can move along V2. But I basically just keep adding more and more V1s and V2s, however I like. And I ask, if I do that, any combination of combining, that's what this is, any linear combination of V1 and V2, where can I get? And in this case, I can get anywhere in the XY plane. So the span of this V1 and V2 that I've drawn here, the span of that is R2, because by adding up different proportions of V1s and V2s, I can make my way anywhere in the R2 plane. So that's what we're saying is basically we're going to take some vectors and we're going to be able to move anywhere along that vector, and then we can add to that moving anywhere along the other vector, and we'll ask where is it that we can get. Let's just show you a different example so that you can see how perhaps it wouldn't be the span. So if I'm here again in, and I have here, and I have just V1, and I say, what is the span of V1? Where can I go just moving in the V1 direction? Then what we'll see is I could go, for example, here, I could go here, I could go here, I could go here, I could go here. So the span of V1 is a line, and we can in fact figure out which line that is, like we did in the last lecture. So this is saying that the span is a special way of saying the span of these vectors is the set of all linear combinations. Okay, so let's then take a look here. We've in a sense already asked this. What is the set W1, which is the span of the standard basis vectors? So I'm taking the two standard basis vectors in R2. That is right here, standard basis vectors in R2, and asking where can I go by adding up multiples of those vectors. And I can go everywhere. I can manage to make it everywhere. I can take some arbitrary point. Let me do that in a different color. I can take some arbitrary point over here, and I could figure out that I could go over here 1, 2, maybe about 3 of them, and then I would go up 1, and I could make it to there. And it doesn't matter which point I pick, I can figure out how to get there by walking along multiples of E1 and then walking along multiples of E2. So the span of E1 and E2, where E1 and E2 are the standard basis vectors in R2, is in fact R2. You can get everywhere. Similarly, if we're in 3 dimensions, nothing is changing. We're able to get everywhere that we want to go in 3-dimensional space by moving along the x-axis some amount, moving around along the y-axis some amount, and then moving along the z-axis some amount. Okay, so we can get everywhere. So here the span of the standard basis vectors in R3 is indeed R3. Okay, so now let's look at so it's in fact this I'm here on this example here that is very similar to this thing here. We have the span of what is the set? W3 equals the span of -1, 4. Okay, so this is, we have this vector. Let's just draw out what it is. -1, 4. There's -1 and 4, so it's somewhat like that. And so we can move along this vector anywhere like that. So it is a line through the origin. It's a line through the origin. Okay, we could actually figure out exactly which line it is, because we can look at it and we can say, okay, so we can pick 2 points on that line. Clearly 0, 0 is on the line. And then what other point is on the line? Well, -1, 4 is on the line, because we are imagining here t times -1, 4. So if I put t to 0, I get 0, 0. If I put t equal to 1, I get this point right here, which is -1, 4, like that. And then I have 2 points on the line, and I could figure out what what line that is, and it is in fact the line y equals minus 4x. Okay, let's take another example. We have here a set W4 indicated to be the span of two vectors. The vectors are in R3 because they have three components. Now, we're first careful to note something. We want to note that these vectors are not multiples of one another, because that's going to be something somewhat different. And when we have the span of this and this, we can move around. But if we had the span of something that looks like this guy and this guy, suddenly we instead of being able to move in 2 dimensions, because we have sort of freedom to move in two dimensions, in this thing we were still only stuck in 1 dimension, even though we may have 2 vectors. And we recognize this situation when one vector is a multiple of the other. So the first thing to note is we want to take a quick look, and we note that 105 is not equal to some number k times 015. How can we tell that? Well, if that was going to be true, for example, for this one to be true, k would have to be equal to 1. And if k was equal to 1, that this wouldn't happen. So we know for sure one is not a multiple of the other. Okay, so that's important. So once we've established that one is not a multiple of the other one here, then the span W4 is all linear combinations of 105 and 015. And how do we write that? We write that this way: t times 105 plus s times 015. First thing you can see is, of course, if t was 0 and s is 0, 0, 0, 0 is in this set. Okay, so it goes through the origin. Goes through origin. Okay, it's an object, a geometric object that is in R3. It has 2 degrees of freedom. It is a 2-dimensional object. It is a plane. So this is a plane. W4 is a plane through the origin. Okay, that is the idea of span. Span is all linear combinations of the given vectors. Okay, next important concept, linear independence. So we got 2 vectors in R3, and then we consider the set, the span of V1 and V2. That is all linear combinations of V1 and V2. And we're going to talk about different vectors. So if we're going to choose different vectors, V1 and V2, and then see geometrically what the span looks like. Okay, so let's just pick V1 here. In fact, I'm going to pick very simple vectors. Okay, here are 2 vectors. Now I'm going to look at the span of these 2 vectors. That is going to be double. I'm going to call that W. It's going to be the set of all vectors. Parameter 1 times the first vector, parameter 2 times the second vector. What does that look like? Okay, so we have, in this case, Z is always going to be 0. And then we'll be able to have any values of X and Y by changing S and T. So this looks like this. Here is Z, here is X, and here is Y. And it is a plane right here. It is the XY plane. That is it. When V1 and V2 are those 2 given vectors, the W formed, maybe I'll just call it W1 so that when we have the next one, it's not confusing. W1 is the XY plane. Okay, now let's look how it looks different if I choose V1 to be the same as it was before, but I change V2, and I change V2 to this vector here. And then I'll call it W2, is going to be the span of those two vectors, which is going to be all linear combinations of those two vectors. And what does that look like? Well, you can see, looking at what these combinations are going to look like, that always the y component is going to be 0. So the y component is going to be 0. We have here x and y and z. The y component will be 0. So we'll be here. It is the xz plane. Okay. We know it's going to be a plane because these are not multiples of one another, and because I've got 2 degrees of freedom. So then we need to think about which plane it is. And in this case, these planes aren't hard to identify. But of course, if we have more complicated numbers, it'll be a plane, potentially through the origin, but it'll be tilted at some sort of angle, much more difficult to draw in 3 dimensions, and more difficult to sort of, just more difficult to draw. Okay, so we're going to stick with sort of easier to draw ones here. Let's do the final version of this. That would be, what if I chose V1 to be equal to 0, 1, 0, and then I chose V2 to be equal to 0, 0, 1. Then W3, our next version of this, is going to be exactly the same, all linear combinations of 0, 1, 0 and 0, 0, 1. And here we've got the situation where no matter what we change S and T to, the X component will be 0. So this, the X component is going to be 0. Let's draw that one out. We have here X, Y, and Z. The X component is 0. So we are here, the YZ plane. Okay, now let us be careful to note this, but imagine this possibility, V1 being 1, 0, 0, and V2 being 2, 0, 0. Okay. So the first thing to notice in this example then is, look, V2 is just 2 times V1. And also you can see that when I formed the span, Y and Z are both going to be 0. Okay, so W, let's call this W4, is going to be equal to this S times 1, 0, 0 plus T times 2, 0, 0. And I could simplify that actually to look like this, S plus 2T times 1, 0, 0. Okay, and I could just, in some sense, then, if you like, replace this by some other number. Okay, I can choose values of S and T, and I'm just going to get some other real number when I do this thing. And so what do I have here? Now I have a geometric object in R3, which has 1 degree of freedom. This is a line through the origin. So despite the fact that we had, the thing to notice here, what we're getting at in this example is, in these 3 cases, we had 2 vectors, and always the span was a 2-dimensional object. In this case, we had 2 vectors, but the span was a 1-dimensional object. And that is because I can establish a dependence of this vector on this guy. They are what we call linearly dependent. So what we want to do is, we want to, when we get a set of vectors, we want to understand, can I make one out of the other ones? If I can, then that one depends upon the others, and I don't get any new information from it. So that is what's motivating this definition here. So we can decide between these 2 cases. So here's the definition of linear independence. If we have a non-empty set of vectors, in this case, there's k of them, in R2 or R3, and this is going to expand up to Rn. the set is linearly independent if the only scalars that cause this thing to add up to 0 are 0. It sounds a little bit, I think this might sound like, it's like, how am I going to tell that? We're going to have a really efficient way of figuring this out. But if we can find constants that are not all 0, then the set of vectors is linearly dependent. Okay, that's the idea here. So we want to understand whether we can make one out of the others. Why am I saying it like that? Because in this case, I could sort of imagine this being put over here. And if they weren't all 0, then I would have a way of making, if all the C's, the little C1, C2 were not all 0, then I would have a way of making VK out of the rest of them. But if they are all 0, that doesn't happen. Okay, so this is the key way of determining, well, this is what it means to be linearly independent. Okay, so let's just do some examples. First thing, it's easy to check for linear independence when there's only 2 vectors. When there's only 2 vectors, you just have to check that they're not multiples of one another. So here, I'm wondering, is 1, 0, 0 equal to some multiple of 0, 0, 1? That's what I'm asking myself. And I see, in order for 1 to become 0, k would have to be 0. But then, of course, that would make this thing also 0. So no, it's not a multiple. 1 is not a multiple of the other. So these 2 here are linearly independent. So the answer here is yes. 1, 0, 0 and 0, 0, 1 are linearly independent. You can't make one from the other. Okay, let's look at the next example. I'm going to ask the same question. There's only 2, so I can do this method of checking for a multiple. So I'm saying, is 0, 1, 0 equal to k times 0, 3, 0? So I wonder, okay, if I multiply, if I put, and so I think, okay, let's just take a look at this middle guy here. It makes it kind of easy. If I set k equal to 1/3, that will be that one will be true. So I think to myself, okay, this line will be true if k is equal to 1/3. Then I check 0 times 1/3, that's 0. 0 times 1/3, that's 0. Sorry, k will have to be 3. Let's yeah, no, k, sorry. Sorry about that. I confused myself here. Okay, here I'm doing this. Yeah. It sort of looks, it's sort of right anyways, but it's here. 0 times 1/3 is equal to 0. 0 times 1/3 is equal to 0. 1/3 times 3 is equal to 1. So there is one number here, 1/3, that makes this statement true, and it works for every component. So so one vector can be made from the other. For example, 0, 3, 0 can be made by taking 3 times 0, 1, 0. That's what I'm saying. Also, in terms of reflecting back on the definition, we have that 3 times 0, 1, 0 minus 0, 3, 0 is equal to 0, 0, 0. So we see here that we have 2 constants, 3 and minus 1, and that this linear combination can be made equal to 0, and both of these are not 0. That is exactly what that definition is telling us. So that these things here are linearly dependent. These ones here. Okay, so let's have just a couple of more questions. If we only have one vector and it's not 0, is the set linearly independent? And the answer is yes, if the vector is not 0. So the answer here is yes, if, and this is in the if u is non-zero. Okay. If u was equal to 0, then C1U is equal to 0 for all C1. Okay, here's another thing. We have two vectors here. They're non-zero vectors. Are they linearly independent? The answer is no. They are not linearly independent. So no, they are not. Let's see why. Linearly independent, or so the other way of saying it, they are linearly dependent. Why? Let's take a look at the definition. Let's imagine C1 times U plus C2 times V plus C3 times 0 equal to 0. Is it possible for this statement to be true when any one of C1, C2, or C3 is non-zero? That's what we're asking here. So what we could do is put C1 equal to C2 equal to 0 and put C3 equal to 10. Then that statement is true. So we have non-zero constants such that when we form the linear combination, we get the zero vector out. Therefore, they're linearly dependent. So a collection of vectors that contains a zero vector cannot be linearly independent. And so let's just write that down. Any collection of vectors that contains the zero vector cannot be linearly independent. Okay, so in general, this is a bit of a summary. If you have unspecified vectors, like somebody asks you, you have some U, some V, some W, and then you get asked something about linear independence, you should be thinking to yourself, what happens if they're same? What happens if they're different? What happens if they're multiples? And what happens if they're zero? Okay, so the answer would change based on the answers to those questions. Okay. Okay, a set with two or more vectors, this is a theorem, set with two or more vectors is linearly independent if and only if at least one of the vectors in S is expressible as a linear combination of the other vectors in S. This is what I actually said informally on the previous page. We have the definition, try to find constants such that they're not all zero. If you can't, then it's linearly independent. And also that sort of means you can make one out of the other, one vector out of some combination of the other ones. That's what this theorem is telling us, going right from that definition of linear independence. It's saying if we've got some set and they're linearly independent, then you can express one as a linear combination of the others. And if you can express one as a linear combination of the others, then the set is linearly dependent. Okay, that is this thing here, if and only if. So some proofs go in one direction and some proofs go in both directions. So this proof, this if and only if means, let me just sort of box in the things here. We've got sort of two statements, this one, and then we've got this statement. So the two statements are sort of in blue here, like that. When you have them connect, these two statements connected by an if and only if, it means if the first statement is true, then the second statement will be true. It also means if the second statement is true, then the first statement is true. And in order to prove these, we prove it both ways. So what we do is we assume one of the statements to be true, and then we show that the other one follows. Then we assume the other statement and show that the other statement follows. Let's do this by example here. So going in one direction, this direction, we will assume S is linearly dependent. Okay, that's the first statement. We've assumed the set is linearly dependent. Now we're going to show that means that one vector can be expressed as a linear combination of the other two. Okay, so we assume that S is linearly dependent. That means by the definition of linear independence that C1v1 plus C2v2 plus ... plus CNVN equals 0, where C1, C2, etc., Cn are not all 0. That's the definition of linear dependence. Okay, let's pick one that is not 0. Pick a constant. We know they're not all 0, so we can certainly pick a constant, C1, C2, whichever one, Cn, that is not 0. Okay, let's just for convenience sake right here assume it's C1. It doesn't really matter if it's C2 or C5 or C whatever. We do, then we just repeat the argument. So we say, okay, we'll, without losing any generality, we are going to assume, or we're going to suppose, in fact, suppose it is C1, not 0. Okay, if it's not C1, then make it whichever one it is. The same argument will follow. Then V1 will be equal to 1 over C1. This is algebra going from this statement here. We know that C1 is not 0, so we can divide through by it. We move everything to the other side and we divide through by C1. Okay, there now our thing is proved, right? We have now expressed at least one of the vectors, in this case now it's V1, is expressed as a linear combination of the other vectors. V1 here is expressed as a linear combination of the other vectors. I mean, this looks like this, minus C2 over C1 V2 minus C3 over C1 V3, etc. Okay, so we have it as a linear combination. There we go. That's the end of the proof in that direction. Now we go in the other direction. We assume a vector, doesn't matter which one, in S is expressible as a linear combination of the others. Okay, so we're assuming the second statement, and we're going to show that the first statement follows. Okay, so V1, we're going to assume that's the one, is expressible as some combination of the other ones. There it is. Then we're going to move everything to the other side. V1 minus C2 V2 minus C3 V3 minus, etc., like that, minus Cn Vn is equal to 0. And we have therefore that C1 is equal to 1. That's the number sitting right here. C1 is equal to 1. So C1, C2, etc., Cn are not all 0. And S is linearly dependent. And we're done. Okay, so we've shown that to be the case. Now I'm going to say something about the proofs. This course is not, we are not going to be doing a lot of proofs. We're not going to ask you to prove a lot of things. However, try to not dismiss the proofs, because if you go through the proofs and really understand why something is true, then you don't have to really memorize it. You're like, oh yeah, I understand why that's true. I've seen why it's true. It has to be that way. So I don't then have it as some sort of abracadabra thing that I remember, and I have no clue actually why it works that way. But I have to always, and that makes it really hard, because after, you'll see in this course, it's going to be extremely difficult to try to memorize many facts. What you're going to have to do is understand why the facts are true, and then you can sort of regenerate them based on that for yourself. So spending some time with the proofs actually gives you, it's not about, you know, trying to convince you that we're right here per se, although it should do that as well. It is more to show you in detail why it has to be this way, to help with the understanding. Okay. There's a corollary to this proof. So the corollary means two statements that just follow immediately from the proof. And the corollary is here, we've got two linearly dependent vectors, then they're parallel. And if you've got two vectors that are parallel, then they're linearly dependent. It's got that if and only if joined between the two statements. Okay, these guys are linearly dependent if they lie on in the same plane. Okay, you don't have 3 degrees of freedom for and have it being linearly dependent. Okay, so that's a corollary to the proof. Let's just draw what B looks like. We've got here X, Y, and Z. And what we're saying is they are dependent if they all lie in a plane. So let's just imagine 3 vectors in the XY plane. This is sort of get a picture of what's happening here. I'm going to go for 3 vectors in the XY plane. We'll have one, say here. These are flat, like you sort of imagine XY being my screen and Z sticking up out of the screen. And we'll have V1 here. All these vectors, V1, V2, and let's just put guy here, V3 here, are all in this XY plane. Okay, it's saying that there's 3 of them. They must be dependent because there are 3 vectors and they're in on what is a 2-dimensional subspace. We're going to get to again to all these words. But you can see actually why they're dependent here, because you could see that I could figure out by moving along V1s and V2s to form V3. So I could say to myself, okay, maybe if I move along V2 like that, and then I move along, let's see here, I got to try to do this here, negative V1 like that, and then maybe another portion of negative V1, I can make V3. So I don't need 3 vectors here in order to maneuver around in this plane. I only need 2 that are linearly independent. And so whereas you can see here, if I only had V1 and V2, I would not be able to maneuver along V1 at all and sort of make V2. Okay, so that this is a statement about how many vectors and what type of space you're spanning and when it's forced to be dependent. Okay, how do we check linear independence? This is a big question, and it's somewhat easy to do in R2 and even in R3 sometimes. And you'll want to have those little tricks for low dimensions in your pocket so you can use them to do things quickly. However, when we're in once we're going to scale this whole thing up, we're in R8 and we've got 6 vectors, and we ask, are they linearly independent? It's going to not be possible to just look and go, oh yeah, I can see that this one's some combination of the others. You're going to have a methodical procedure for doing that, and we will get to that. Okay, but let's just here do a couple of examples in low dimension without the heavy hitting algorithm, and then we can see how this is working. So we're gonna start in R2. We're going to ask, are these 2 vectors linearly independent? So what we're asking, does C1, C2 non-zero exist such that C1 times the first vector plus C2 times the second vector equals 0? Is it possible for me to find C1 and C2 to make that true? So this is effectively 2 equations and 2 unknowns. I can write this out like this. Going along the top row, I'm going to write this out, and that's going to be 5C1 minus C2 would have to be equal to 0. And 4C1 plus 6C2 would also have to be equal to 0. Okay, this is something we've all done before. We've got two equations and two unknowns. Let's see if we can find a solution. So here we have C2 equals to 5C1. And then I'm going to substitute that down here, 4C1 plus 6C2, which is 5C1, is equal to 0. That means, and the only way that could be true is if C1 is equal to 0. And then that also means that C2 is equal to 0. So the only solution here is both of them are 0. That's telling me that these things are linearly independent. Yes. These are linearly independent. Okay. All right, let's try another example. What about these three guys here? It's the same question. Can we find non-zero constants? So can we find non-zero constants such that C1 times 101 plus C2 times minus 101 plus C3 times 202 equals 0, 0, 0. Is it possible for us to find non-zero values of C1, C2, and C3 to make this true or not? Now we've got here 3 equations and 3 unknowns. Okay, we're reading off of the top row. I'm going to just circle it to make extra clear what I'm doing. I'm reading off this. And then I'm going to read the second row and the third row. So here I've got C1 minus C2 plus 2C3 is equal to 0. I've got 0 times C1 plus 0 times C2 plus 0 times C3 is equal to 0. And I've got C1 plus C2 plus 2C3 is equal to 0. Okay, so I'm looking at this 3 equations, 3 unknowns, and I'm going to say what values of C1, C2, and C3 solve this. So first, I don't get much out of this, and maybe what I'll do right off the top is I'll then take let me think here. I'm going to take this equation 1 and equation 2. Why don't I take equation 1 and subtract equation 2? That's going to give me 2C2 equals 0. Okay, so this is going to be 1 minus 2. C1 minus C1 is 0, minus C2 is minus 2C2, and then 2C equals 0. So I figure out that C2 is equal to 0. Okay, and then what? I have that C2 is 0. So let me just write that. Then that's why I'm down here. C1 plus 2C3 is 0. And C1 plus 2C3 is equal to 0. That's the remaining, those are the remaining equations with C2 equals 0 substituted in. Okay, so I can see actually there's really only one, well, there's really only one equation here now. And what I can see then is that C1 here is going to have to be equal to minus 2C3. So once I pick C3, let me just say I pick C3 to be, you don't know, just can pick it to be anything. C3 could be equal to 1. Then C1 will be equal to minus 2. And I have, in fact, a constant, adding in that C2 is equal to 0. So I have C1, C2, C3. That makes this statement true. And notice that not all of these are 0. So then that means that these vectors are not linearly independent. No, not linearly independent, because I was able to find non-zero constants to make this true. And then I can even, yeah. So what have I found? Let me just write this out. I'm thinking I have found that minus 2 like that, plus 0 times this, plus this. I have found that out, and this is not 0, and this is not 0. There's a 1 there. That is not 0. And yet the whole thing adds up to be 0. So clearly I can make 1 out of the other 2. Okay, so now we've established in this case that the vectors were linearly independent, and we've established in this case that the vectors were not linearly independent. Now let's talk about what the above vectors span. Okay, so here the span of this guy here, 1, 0, 1, minus 1, 0, 1, 2, 0, 2, is going to be exactly the same as the span of 1, 0, 1 and minus 1, 0, 1, because this guy here is simply a multiple of this guy. So I do not need that guy. I can clearly make V3 there as 2 times V1. I don't get anything out of that. So I can eliminate him. Those two spans are the same. And then I can notice that one of these is not a multiple of the other. So there's no way I can make this guy here, the second vector here. I can't make him by multiplying by a constant times the first vector. So these two are linearly independent. So therefore I've got 2 vectors that are linearly independent. And then when I ask what the span of that is, there's 2 degrees of freedom. The span is all linear combinations. Okay, 2 degrees of freedom. It's a 2-dimensional object. There's no constant term. And so here we have a plane through the origin. Okay, and then this question is, yes, we can. I mean, I've already answered this question. Yes, that is 2, 0, 2 is equal to 2 times 1, 0, 1 plus 0 times minus 1, 0, 1. Okay, we found that out when we solved our 3 equations and 3 unknowns. You can express one of the vectors as a linear combination of the other, and they are linearly dependent. Okay. No, you're maybe doing more than imagining this. We need a more efficient way to do this. Clearly, and particularly when the number of vectors gets larger and the dimension, the number of components at each vector gets bigger, we need to be more efficient. And indeed, we do have a more efficient way of doing this. That is going to be coming in a further lecture. Okay, so far we've talked about 2 really important concepts. We've talked about span. We've talked about linear independence. Our final thing that we wish to define today is basis. Okay, a set of vectors is called a basis. So we imagine we have a collection. A set is just a collection. We have some collection of vectors, and then we want to know, is this a basis for R2 or R3? And so it is a basis if the span is R2 or R3 and they're linearly independent. So to have a collection of vectors to be a basis, both of those conditions have to be met. It has to span the space and the vectors have to be linearly independent. Okay, so here, for example, prove that the set, here's a set of 2 vectors, and we want to prove that it's a basis for R2. Okay, so we have to do 2 things. We have to prove that it spans R2. So if we want to prove that it's a basis, we have to do 2 things. We have to show that it spans R2, and we have to show that the vectors are linearly independent. Okay, those 2 things together tell us that this is a basis. Okay, so let's first show what would we do? We want to show that these 2 vectors span R2. It means that what it means is, can we take linear combinations of these 2 vectors and get wherever we want in R2? So we imagine going to some arbitrary point in R2, X and Y. So just pick some point in the plane, X and Y. And we're asking, is it possible to get to that value of X and Y by taking some combination of these two vectors? That's what we want to show. So again, I'm going to separate this out into two equations, and then I'm going along the first row. That's going to be, can I write X as minus C1 plus C2? And will I be able to write Y as 2C1 plus 5C2? Okay, so let's think here. This first thing here means C2 is X plus C1. That's rewriting the first equation there. And then the second one is that C2 is equal to Y minus 2C1 over 5. Both of these things here are C2, which means the right-hand side are also equal. So that means we could write Y minus 2C1 is equal to 5 times X plus C1, or 5X minus 5X plus Y is equal to 7C1. So I could choose C1 to be equal to 1/7 minus 5X plus Y. Then I'm gonna take this value of C1 and plug it back in right here. So that will allow me to compute C2. So C2 will be X plus 1/7 minus 5X plus Y. And that is going to be 2/7 X plus 1/7 Y. Okay, let me just rewrite that out. So what I'm imagining is I take any point in the plane, X, Y. And then I'm asking, can I find C1 and C2? And I'm saying, yes, you can. You give me any X, Y, and I will tell you, use C1 equal to this, and use C2 equal to this. Okay, and then that means that I will be able, and then I will put that here, and then I will be able to get to that value of X, Y that you told me about by going along this much of the first vector, this guy, and by going along this much of the second vector, this guy. So yes, it spans R2. So therefore it spans. I was able to find C1, C2 in terms of X and Y. So therefore, the set spans R2. Okay, now are they linearly independent? Well, there's only two of them, so I'm just going to check one is multiple, if one is a multiple of the other, and there's no way that I can do this. There is no value of k that will make that true. So -1, 2 cannot be equal to k times 1, 5. So therefore, they are linearly independent. And so therefore, the set is a basis. Okay, span plus linear independence. Okay, next thing we're going to just note, and we're definitely coming back to this. This is going to have much more detail later in the course, but just to plant the seed and see what's happening here. Let's just take a look at the vector 3, 4 in relation to the standard basis and in relation to the basis above. What does that mean? Okay, so what is our standard basis? Our standard basis is 1, 0 and 0, 1. We're in R2. We're doing here with a 2-component vector. Okay, so let's just draw a picture. We are here. We are at the vector 4, 3. So, sorry, 3, 4. So we're here 1, 2, 3, and 1, 2, 3, 4. So here it is right here. Okay, there it is, 3, 4. Okay, and now we have, I'm going to add to this axis here the standard basis vectors. There's E1, that's this guy here, E1, and then here is E2, and that is E2. So what we're saying is, if I consider this vector here, 4, 3, in relation to the standard basis, what I'm thinking of is I can get to the position 3, 4 by doing what? By going 3 times along this guy plus 4 times along this guy, right? I can go like this, 1, 1, 2, 3. That's this 3 right here. And then I can go like this, 1, I'm taking this guy here, 1, 2, 3, 4. In fact, when we write our vectors like this, we are basically saying how much of each standard basis vector we need to get there. We just haven't really thought about that before. Okay, now let us take this same point 3, 4 in relation to the basis above. Okay, I'm going to draw a picture of that and then I'm going to go through this. Okay, we're talking about the same point in space. 1, 2, 3, 1, 2, 3, 4. We're talking about the same spot here. There it is, 3, 4. Okay, now our basis vectors are looking different. Our basis vectors, let's observe what they are from the previous question. Our basis vectors are v1 equaling minus 1, 2, and v2 being 1, 5. So let's just draw those on our drawing. 1, 5. So this is 1, and we've got to extend our. This is 1, 2, 3, 4, 5. So 1, 5 is right here, and we have over here minus 1 and minus 1, 2. So this guy here is v2, and then we have over here minus 1, 2. That'll be right here. So we have another vector here, and that is going to be v1. Okay, so now we're asking how many times do we have to go along v1, and then how many times do we have to go along v2 until we can end up at 3, 4. Okay, but we already calculated out how to do this. We calculated out that any value xy, right, it is going to be equal to 1/7 times minus 5x plus y minus 1, 2 plus 1/7 2x plus y multiplied by 1, 5. Okay, so in this case, now xy, we have that x is 3 and y is 4, because now we're talking about this specific vector. So we simply put in those calculations to say that 3, 4 will be equal to 1/7 times minus 5 times 3 plus 4, all times minus 1, 2, and 1/7 times 2 times 3 plus 4 times vector 1, 5. Okay, and that is equal to minus 11 over 7. So we're here still 3, 4 is equal to minus 11 over 7 into times minus 1, 2 plus 10 over 7 multiplied by 1, 5. So what we're saying is we can go here, get a different color, red. We can go minus 11/7. So that's about kind of 1.5 minus 1.5 times on this guy. And that is v1. So we come down here minus 1 of v1 and about a half, minus 1.5 on v1. And then we go here 10/7, about 1 1/3 on v2. So I'm taking this new line, taking this guy, I'm drawing it parallel, and I'm going to go 1 1/3. So we're going to go, we went here, this scaling factor on v2 is minus 11/7. Now I'm going to go 10/7. There. These two guys are parallel. Okay. So what we've now done is figured out how to walk to 3, 4 in a different way than using the standard basis vectors. We used these basis vectors, and then we had to walk this far along each one of those. Okay, so what we then say is these numbers here relate this vector to this basis. You don't have to actually use a standard basis. Just going to make that final point. I've said this before, but just to emphasize this, when we say 3, 4 and nothing else, then we are assuming the standard basis, but it does not have to be that way. Let me give you a quick analogy. What happens when I go like this? You're like, hey, that's number 7. I hope that's what you do. And then that to you should indicate, pictorially this. There's 7 little rocks on the ground. Now, that is when this number is a base 10 number, right? If I was going to represent that in, say, base 3, I would write it like this, which would be equal, whereas I'm thinking like this, 2 times 3 plus 1, okay, that. And then when I said this, you would not think to yourself, there's 21 stones on the ground. You would think, oh, it is relative to the base, 2, 1, relative to the base. This is still 1, 2, 3, 4, 5, 6, 7. 2 groups of 3 and 1 left over. This here is 1 group of 7, right? And I could go like this and say this numeral is relative to the base 10. This numeral is relative to the base 3. Now, when I choose to just go like this, we normally operate in base 10. So then we just assume, oh, it's relative to base 10. But it does not have to be that way. And this is the same thing here. When we give a vector, we're basically saying, hey, we're assuming this is relative to the standard basis, but it does not have to be that way. It could be, we could give constants relating it to a different basis. And then of course we would have to tell you what that is. Okay, there's a lot in this lecture: span, linear independence, and basis. And likely these are quite new concepts. So take a bit of time, read through the textbook, and bring your questions to the Zoom sessions. Thank you very much.